In example 4, we're looking at a machine that loads coal into different train cars. We're told this machine loads cars with a mean weight of 75 tons and a standard deviation of 0.8 tons. And we're told that it also loads the cars with a normal distribution. So with that information, we're going to look at two different situations and calculate two different kinds of probabilities. The first one in part A is something that we've done before. We're asked to find the probability that one car chosen at random ends up being loaded with less than 74.4 tons of coal in it. Well, finding this probability is just like we have done in the past few examples. If we consider that the weight of the cars is normally distributed with a mean of 75 and a standard deviation of 0.8, we're looking for the probability that a car will be less than 74.4 tons of coal in it. That probability would be represented by the shaded region on the normal curve, and I can find this area by finding the equivalent area on the standard normal curve. I need to convert my value 74.4 into a z-value, and that ends up being negative 0.75. So to get this area, I'm finding the probability z is less than negative 0.75, which is an area to the left of that z-value. That area can be found on our normal table directly, and it ends up being 0.2266. Basically, the probability that a car loaded by this machine would end up with less than 74.4 tons of coal in it is over 22%. So while it's unlikely, it's not really completely rare to happen. Part B asks a little different question. We have to note the difference here. In part A, it asks me what's the probability that one car chosen at random will have less than 74.4 tons of coal. In part B, it's asking me what is the probability that 20 cars chosen at random will have an average weight of less than 74.4 tons. This is a much different question. I want to know the probability that the mean of 20 cars chosen at random will end up being less than 74.4. What I can tell you is that this is very much less likely to happen. We can think about it in terms of the example we used in the lesson today. We talked about the fact that if we were getting the average height of Bunker Hill students, if we found that average height to be 5'9", and then I asked you what's the probability someone's over 6'2", well, it might not be likely, but it's probably not that rare. But if you think of the question whether or not 20 students chosen at random would have an average height of over 6'2", well, then that's much less likely to happen. So to solve this problem in part B, what I'm actually trying to find is the probability that this sample mean of size 20 is less than 74.4 tons. And the way I'm going to do this is I'm going to use what's called the sampling distribution. So what I have here is a normal curve, but this is not a curve of the single cars. This curve contains the data of sample means of size 20. So think about the normal curve in part A like a big sand pile where every grain of sand represents one individual car being loaded with coal. In part B, in my sampling distribution, each grain of sand represents one set of 20 cars being loaded. So the population in this case is theoretically every different combination of 20 cars that exists. Every single combination of 20 cars has a mean weight, and those weights are shown in this distribution right here. We can see that the spread, number-wise, is a lot more narrow than it was in part A. And that's because there's a different standard deviation for this set of data. So there are similarities between the population of cars being loaded with coal and the population of sets of 20 cars being loaded with coal. Both distributions are normally distributed. The mean of each distribution is actually the same. So the mean of the cars was 75 tons, and the mean of the groups of 20 is also 75 tons. However, the standard deviations are different. They're different but related. The standard deviation of this sampling distribution is equal to the standard deviation of the original population divided by the square root of the sample size that was used to create it. What this allows me to do is this allows me to treat the problem exactly the same way as in part A. But when I'm picking one value out of a sampling distribution, that one value actually represents a sample mean of size 20. So getting the probability that the sample mean of 20 cars is less than 74.4 tons of coal, I'm going to use a similar equation for Z, but I'm using the mean and the standard deviation of this new set of data. Now the mean of that set of data is the same, but the standard deviation, as we mentioned, has changed. So converting 74.4 to a Z value this time, I would do 74.4 minus 75, just like I did up here in part A. But my standard deviation is now not just 0.8, but 0.8 divided by the square root of 20. This gives me a Z value of negative 3.35 in this problem. That is way down here on the left side of my range. The amount of area under the curve to the left of that Z value is essentially nothing. If I look up negative 3.35 on my normal table, negative 3.35, I get an area of 0.0004. What this is saying is that while the likelihood of one car weighing less than 74.4 tons is about 22%, the probability that I could get 20 cars to average out to less than 74.4 tons is almost zero.